Welcome back to our series on statistical methods. This is the lecture 1, and we're going to do chapter 1, the introduction, and the textbook we are using is called Design and Analysis of Experiments, the 8th edition by Douglas Montgomery. Okay. Now, since this is the first video officially of this class, there is no review. Let's go over chapter 1 and see what's going to be in there. We're going to talk about what an experiment is, the types of statistical models that we have, a brief example of an experiment, processes, types of processes that we have, what objectives we have for an experiment. There are 3 basic principles of experimental design that we're going to talk about. And then we're going to talk about some experimental strategies that are used. Some are commonly used, they're good, and some are not good. And then we'll go over the guidelines for designing experiments. Now, I want to say that in this course, we are going to be statistical because this is a statistics course. So we're going to be focusing on the analysis of variance, not on the design of experiments. You might say, what's the difference? Well, experiments should be designed in a group setting, which should contain a subject matter expert. Now, whether the subject matter expert should be the leader of that should be determined by the individual organization or project. And that's based on that person, how willing they are to embrace statistical methods and the group input. So you need someone to lead the project who is willing to take input from all members in all areas and incorporate it as needed and come up with the best result possible, regardless of personal feelings or philosophy. Okay? So, our goal when we're doing experiments, let's see, I'll talk about that in just a minute. So first, there are 2 types of studies that we deal with in statistics. The first is an observational study, and we don't interfere with the outcome of whatever we're measuring. We may be measuring a process or a procedure, and we're just simply collecting the data. We're not doing anything to influence the outcome. Okay? Now, experimental design or experimental study, that is set up with specific parameters that are changed in order to determine the effects of those changes. And we'll talk about some of the goals and reasons that we perform experiments, but we want to know and observe the effects of the changes in the input variables. So here's a definition of an experiment. You could say it's a test, or it could be a series of tests, sometimes called runs, depending on what you're doing, or trials, in which we make deliberate changes to the input variables of whatever process or system we are measuring. And the reason that we want to do this is to mainly determine the causes for variation. We could also want to determine the location of or the centering or target value. We want to move something closer to the target value in the output. And we want to develop a model that can be used to improve the process or system and in decision making. And a lot of times we will take this a step further and develop a model for predicting the output. We can. I don't say a lot of times. I shouldn't say that. Sometimes. So sometimes sometimes what has happened is I've performed a design experiment and I've used certain settings within a continuous variable. So there may be a low, medium, and high. And maybe it's a continuous variable, so I could change that dial to any value, basically. But because of the design, I only chose 3 different values. Those may not be the optimal values. So I can then take the results and maybe come up with a regression equation, maybe a multiple regression equation, where I can see what value of and of that regression equation will maximize my output variable or minimize my output variable depending on what I'm measuring. Okay, so that is something that we can do as well. Okay, so the goal of the experimentation is to learn how to, our goal in this section is to learn how to plan and conduct experiments, analyze the results, and obtain objective conclusions. Again, we are not going to focus on the planning and conducting of experiments except in this first chapter, and so this is an introduction, and you should know where to go if you ever are charged with designing an experiment. Okay, come to this book, chapter 1, and then there are reference materials that you can go see from there. All right, so the benefits of performing these experiments is we can reduce the time to design or develop a new product or a process. We can improve the performance of an existing process. We can improve the reliability. Reliability is how long it, or how often or how long it takes for it to break down, or how the type of breakdown that occurs in something, or you could call it the performance of the products. And we want to achieve maybe product or process robustness. Robustness, one way to think of robustness is if I have a robust process or design, let's say a robust design, if let's say this flange is used to secure something, and slight variation, the variations in the flange, if it's robust, variations in that flange, say width, will not affect its strength or function. That would be a robust design. Okay, example of it. So we want to be able to evaluate materials, alternate designs, or even settings or tolerances for maybe a system or a component. Now, I do need to say that I've taken items from the PowerPoint slides provided by the publisher, which is Wiley for this book. So I have incorporated some of the publisher provided slides into these slides in my lectures rather than recreating the information. Okay, and so you're seeing these figures from the book and from those PowerPoint slides. So we have here a depiction of a process, and so we have inputs. This may be considered raw material, and for those inputs, there may be controllable factors. We'll denote those with X, and I think we have P of those in this case. And then we can have uncontrollable factors. This might be the temperature or humidity if it's an uncontrolled environment. And we denote those with Z's in this text, and I'm not really sure what this letter is, how many we have here. I have that written down somewhere, but I don't see it right now. Okay. And so we have all these things feed in and become part of the process, and they give us what we're interested in is the output. I want to comment that the author is not necessarily a statistician. He's more of an engineer and very good at what he does, and this is a very good book. For us statisticians, the notation is somewhat backwards. Random variables we like to use capital letters, and observed values we like to use little values. And the author basically reverses these. So if you're getting confused, that may be why. So just remember that depending on what subject you read and who the author is, they may have reversed something or not followed the standard practice of statisticians, okay? And that's the case here, which as long as you keep that in mind, it shouldn't affect anything. You just remember that it's reversed in this situation. All right, so what kind of models are there? There are mechanistic models, and we usually think of these types of models when we think of models. We think of maybe physics, and the example is force is equal to mass times acceleration. This is a law that we know, and we know that this relationship holds, and it's a physical mechanism or phenomena, And it's so well understood that we can get useful results using this mathematical model, and we can develop things directly. In real life, if you try to measure this, you're going to find that you do have variation. There's measurement error. There may be some type of vibration in the background that's affecting something. It may be a little different based on different temperatures, etc. But that doesn't change that this is a fundamental law, physical law that occurs. But when we get into complex situations, we often don't know these mechanistic models, and we don't want to have to take time to even think about learning them. So what we do instead is we use empirical models, and empirical models are most powerful when we apply statistics to them, and thus give ourselves some confidence level associated with the model. Okay? And so we determine these by well-designed experiments. Poorly designed experiments will give you an empirical model that's not very useful. So well-designed experiments are very important. Okay, so here's a quick example of an experiment. Maybe a metallurgical engineer wants to determine whether they should use, his or her company should use oil or salt water to quench this certain aluminum alloy. And so what they're going to do is they're going to take test coupons. A coupon in this case would be pieces of usually the same size piece of the alloy. Usually a rectangle, but it could be a circle or something else that they cut out or stamp out or make. And so they're going to take these coupons, and some of them they're going to quench using oil, and some of them they're going to quench using salt water. Obviously, if you're hardening something, once you've hardened it with one process, you can't then harden it with the other process. You need a different sample. So you can't do both to the same subject. You have to do this to different subjects in this case. And so what they're going to do is they're going to measure the hardness of these coupons after they have quenched them. And they're going to take the average hardness and try to determine which method is or medium, if you will, the salt water or the oil, is the best for quenching and hardening this aluminum alloy. So here's some questions that naturally arise. Are these the only two methods? Or are these the only two methods that we want to consider? Are there other factors? How many coupons do we want to subject to each method? How are we going to determine which coupon gets salt water and which coupon gets an oil quench? How are we going to determine the order in which this occurs? Once we get the results, what data analysis method are we going to use? And once we get the analysis, what's a significant difference between hardness for these two methods for us to decide we want to use one over the other? Okay. Now, I want to point out here that there is a difference between statistical significance and practical significance. If we have a weight loss program and the subjects, there's a placebo group and a test group that's actually receiving the diet, and so there's this weight loss program, so it's a diet pill, and so people are randomly divided between the two groups, and we measure the weight loss or gain of both groups and over those 3 months, and we want to know if there's a difference in the diet group versus the placebo group. And we find that there's a statistically significant difference in the weight loss between the two groups, but the difference of weight loss is 1 pound over 3 months. So while this may be statistically significant, it's not practically significant. No one's going to go out and spend money on a weight loss program in which they only lose 1 pound over 3 months, on average, by the way. So I want you to keep that in mind. Statistical significance doesn't mean practical significance. All right. So our objectives are, we wanted in an experiment is to determine which variables are, we call them factors, because even if we have something that's continuous, we're going to break it up into levels or categories. Okay. So which variables or factors have the most influence on our output? We also may want to determine optimal settings for those most influential and controllable variables or factors. And we do this for three reasons. One, we may want to get the value of y as close as possible to the target or nominal location. We may also, and usually we do want this, we want to minimize the variation of y once it's set. So we don't want it to vary more. We want it to vary less. So we want to optimize these settings so that we have a minimal amount of variation in our output. And we want to, or we may want to minimize the effects of some uncontrollable variables or factors so that they don't influence the output as much as they have in the past. Okay. So now, let's talk about three basic principles for experimental design. Okay. So the first is randomization. So we're going to randomize the allocation of the experimental material. We're also going to randomize the order in which we run the experiments. And so this usually helps us satisfy the requirement that the observations are independently distributed, random variables, okay? And so there's not an effect between one run and the next, okay? So how do we do this? We use a computer program to randomize these. That's the most effective way to do it, okay? So we want to run them in a random order, and this will balance out the effects of what we call lurking variables, variables that may have an influence but that we're not interested in studying, okay? Now let's talk about replication. That's the second principle. So a replication is an independent, repeated run of each of the combination of factors. And so this allows us to estimate experimental error, okay? So we can estimate the experimental error, sometimes called background noise, okay? It also, and by estimating this, we also improve our precision when we estimate the effect of something, okay? And so it improves the precision of the parameter estimates for the mean response, which would be y bar. And we want to make sure that you know that replication is not the same as repeated measurements. Repeated measurements occur on the same experimental unit. In our last example, the experimental unit was the coupon, the test coupon of the aluminum alloy. And as we mentioned, we can't repeat the experiment on the alloy. Once it's hardened, it's hardened. And running the process again is going to have a different effect. It may harden it a little bit more, but it's not going to be the same as hardening it from raw material. Okay. So the third principle is called blocking. Okay, and this is a design technique that improves the precision of our comparisons among the factors of interest. Okay, and we use this to reduce or eliminate the variation that's contributed by something we call nuisance factors. Okay, so a nuisance factor, it may affect the experimental response, but it's not of interest. Okay. So a block is a set of relatively homogeneous experimental conditions. For example, two batches of raw material, they may have different thicknesses, so each batch is a block. So within each batch, you may have a consistent material thickness. So then half the runs or tests would be assigned to each batch or block so that each of the other factor level combinations are treated are tested on each block. And so this is a complete random block, is what it's called. And so these are the three principles that are part of every experiment. Okay? All right. Now, let's talk about some strategies for experimentation. some strategies for experimentation. So we have a best guess experiment. So what happens in this? We perform an experiment and measure the result. So the example may be that we're playing a round of golf. And based on the result, we change one or more factor levels. So the example here may be that we switch the driver, from the regular to the oversized or vice versa. And then we keep on doing that until we are, quote unquote, satisfied. Okay. So as the author says, this is used a lot. And in some cases, this might be actually more successful than you suspect it might be. And that would be because of subject matter expertise and experience. In my last job, I had been in supervisory positions for over 20 years. And so my boss, who was the owner of the company, really had not been day-to-day supervising people. And so he would come in and be unhappy at times about a certain, the way the company's discipline was applied to a certain person, which was always fairly applied and consistently applied, but he might think that the person deserved, a second chance or, a little less harshness or maybe something along those lines. And of course, the problem with that is fairness. You have to, if you punish one person using the policies, you have to do it for everybody. If you make an exception for one person, you have to make it for everybody. So he would come in, he would say something, and I would say, if you do this, this is what's going to happen. And this was based on just seeing this situation over and over and over again through the years. And so I knew I could tell, what was going to happen. And he'd say, you're wrong. I don't know why you're thinking that. You're being negative. And then I would say, okay, we'll do it your way because you're the boss. Do that. And then the outcome that I predicted would occur. And so this kept happening. I wasn't paying much attention to it, but every time he'd come in, I'd say, yeah, this is what, every few months or what have you, I'd say, okay, but this is what's going to happen. And so he came to me after about a year of this and said, and he was upset. He says, you were right every single time. And he's like, I can't stand it. You're right every single time. And it's based on subject matter expertise and experience. Okay, so I didn't have to perform an experiment in that because I'd seen this situation over and over again and I had observed it and I could just tell which way was going to happen. But if I wanted to improve the situation, I couldn't have used this best guess or this experiment. I really need to do a statistically designed experiment to improve the situation if I wanted to affect it. This was just observational, okay? So there are many disadvantages to this. This requires a high level of technical and or theoretical expertise for the process. So I would never do this in a manufacturing process. I would always do the statistical analyses. And it requires a high level of practical experience with the process. So there's very few people that meet these requirements. The third disadvantage, and this is the most importantly, if the first guess doesn't produce the desired result or close to the desired result, the experimenter has to take a second guess, and this could continue for a long, long time, and there's no guarantee of success. This could be very costly and very harmful to the reputation. Fourth disadvantage, there's no rule for when to stop the experimentation. Fifth disadvantage, there's no method to guarantee that the optimal solution has been achieved. So please don't use this method unless you're forced to do so by someone else, like your boss or something, okay? So this is a bad method. The next method is called OFAT. I've never heard it called OFAT, but I have heard it one factor at a time experiments. And so what they do here is they select a starting point or baseline. set of levels for the input variables, okay? And then they perform one experiment at each level of one factor, and they hold all the others constant at the baseline levels. And then they repeat this for each of the factors. So you would basically create a separate graph for each factor and select the best, what you would think is the best setting for each factor. So here's the example with the golf. Let's say we have the driver, and we have oversized and regular sized. And let's say it was something like this. And this is the score, golf score. And then here we might have the ball. And so there's the balata type, and I don't know what that is. And then there's the three-piece type. And let's say that was almost no difference between the two. And then how we get around the golf course or transportation. So we could walk or we could ride the cart. And let's say that we saw this, which would be surprising, but that's what the author saw when he did this. Okay, and then there was beverage, and we had water, and we had beer, and surprisingly, he saw this. Okay, so in this case, we would choose the oversized driver. We wouldn't care about which ball it was, but we would choose walking. And, the beverage was Gatorade. I'm sorry, this is beverage. This was beverage, and it wasn't beer. It was Gatorade. Okay. I was wondering why you do better with beer. Usually I do worse. Okay, so we'd choose this. But this doesn't consider that there might be interaction between these factors. So at certain levels of these, we may perform worse by choosing these values here. By combining them, we may perform worse than we would with another combination. Okay? So this is a bad method. Again, this is not desirable. It's very inefficient, and even though it's associated with the scientific method, it's a very limited and inefficient and costly way to do things, especially if you have interaction. And the third way is a statistically designed experiment, and this is what we're going to investigate, and this is based on R.A. Fisher's factorial concept. So what's a factorial design? Okay, so all the possible combinations of factor levels are tested at once, at one time, at same time. And so this is the most efficient way to do an experiment. And so for the golf experiment, we have all these factors. Okay, there could be more, but these are the ones that he's listed. The type of driver, the ball, walking versus riding, type of beverage. This was water versus Gatorade. I've got to remember Gatorade, so you stay, okay. Time of the day, weather, type of golf spike that you're using on your shoes, all different sorts of things. And so for the type of ball, here's a two-factor experiment where we've got the type of ball and the type of driver. And these are the scores, okay? So we put scores at each, this is not the score, but we put scores at each of these values, okay? So for each of these combination levels, for B and O, we'd have scores here. And for R and B, we'd have scores there. And for T and R, and for T and O, okay? So let's actually look at this and see what the results were, because our author actually did this, went out and did two replications. So for each set of conditions, played 2 rounds of golf, and there are the scores for each of these. And so this is how we can represent this with a picture, pictorially. Okay, so let's look at the type of driver here versus the type of ball. And so here we're going to compare the type of driver. So the regular, what we would do is we would average the scores for these two and compare them to the average scores for those two conditions. So for regular versus oversized, okay? And then we would want to compare the type of ball. So we would average the scores for the balata type ball and then compare them to the average of the three-piece type of ball. But then for the interaction, this is the interaction effect, we would take these scores and compare them to these scores. So here we have the balata oversized versus the regular three-piece ball. And then we take the three-piece oversized compared to the regular balata type. So we would see if there's an effect of the interaction based on that. So here are the calculations. I won't go over them, but for the driver effect, again, we maybe I can get those in there. So we're going to take, for the driver effect, we're going to, oops, I hit the wrong thing. We're going to take these scores for the driver, the regular, and average them and then subtract these, okay? And so that's what we've done, and we see that this was the regular and this was the oversized. Now remember, so this means that on average, he scored 3.25 strokes higher using the regular driver than he did the oversized driver. And remember that a lower score is better. So in this case, you would want to choose the oversized driver, assuming that this is significant enough difference for you, or practically enough that 3 strokes is meaningful. When you're playing golf at around 90, 3 strokes is not all that significant. If you were playing golf around 70, the 3 strokes, then that's championship level. 3 strokes is very significant. 3 under par is much, much better than par if you're in a tournament. Okay, so it depends on how good you are and as to how significant this might be to you. Okay, then the ball effect. So for the ball effect, again, now we take for each type of ball, we average for the balata type, all the scores for that, and we take all the scores for the three-piece type, and we subtract them. And let's see, 88, 91, 92, and 94. So that's the three-piece type. And then for the balata type here. And so we see that the three-piece type is higher on average by 3/4 of a stroke. So again, that's less than 1 stroke. That's not practically significant. It might be statistically significant, but it's not going to be practically significant. And so since this one is higher, we would, if we wanted to we would choose the balata type in this case, if we just looked at the fact that which one was smaller. But again, they're so close that it may not be statistically significant. And then we look at the interaction, and we take, in this case, we're going to, first we're going to take these, whoops, we're going to take these, I'll use a different color, and then we're going to subtract the average of those and see what the difference is. Oops. And the average distance is 1/4 of a stroke, so really insignificant, close to 0. So we would say that in this case there's no, well, we'd have to test it statistically, but it's probably going to come out and say there's no statistical difference or interaction between ball and driver. Okay? Now, this is for a 2-factor. For a 3-factor, let's say we now have beverage, driver, and ball. We could represent this with a cube. We can do 3-dimensional. But what if we wanted to go to 4 dimensions? And so now we're going to add mode of travel. Well, one way to do that is to depict it as 2 cubes, one for walking, one for riding, and then each of these would be the cube for the beverage, ball, and driver. And so this would be a 4-factorial experiment. Okay, and now let's talk about a fractional factorial experiment. This is going to be a lot of different combinations up here. This is going to be a very intensive experiment with a lot of possible combinations. So if since there's only 2 factors, it's going to be 2 to the 4. So 2, 4, 8, 16. So there's going to be 16 different possible combinations. If you're going to do replications quickly, this is going to become a large experiment if it's a factorial design. So maybe it doesn't make sense to look at some of these combinations if you're walking versus if you're riding. So we look at some of the combinations here when we're walking, and we look at the other combinations when we're riding. And then that would be called a fractional factorial experiment. Okay? So hopefully that gives you an idea of how we would set these up. And then again, this is just a introduction. So we don't expect you to have all of the, to memorize this or have everything all down pat for this. Okay. So now let's talk about the guidelines for designing an experiment. So, first is we need to recognize the and state the problem. So here we would want to talk about who, what, when, where, why, how many. You want to be thorough or you're going to pay the price later. I speak from experience, lots of experience. So many times when I was not leading the design and I lobbied for this, people would say, there's no need to do that. We're just wasting time. We already know all that. But usually we don't. We need to be thorough. Who, what, when, where, why, how many. As many of those as you can answer in as much detail or in depth as possible. Okay? Where. Okay. So this step is often skipped or half done, and it causes a large portion of the experimental results to be useless or incorrect or of much less value than we want them to be. Then we need to choose our factors, levels, and ranges of the variables. Okay? So we need to verify that the selected variables measure the characteristic of interest. This sounds simple, but it's not always that way. Okay? And then we need to determine how we're going to measure these. So measurement equipment that we have available, is it reliable? Is it repeatable? What, in statistical terms, what's the bias or variation or calibration of the material, of the equipment and its capabilities? Okay. So, I'm sorry. So I mixed these up. This was choice of factors level. I just talked about selecting the response variables, didn't I? Okay. So now let's talk about the choice of factors levels. So we need to look at the design factors, blocking factors, nuisance factors, lurking variables. We need to hold which factors are going to be held constant, which are going to be allowed to vary. And as I said, the selection of the response variables have to do with these variables measure the characteristic of interest, and that we determine how we're going to measure them. Okay, so what are nuisance factors? There are controllable nuisance factors and there's uncontrollable nuisance factors. And so controllable can be set, the levels can be set by the experimenter. Uncontrollable factors, nuisance factors, we say that if its effect can be measured, then by using a method called analysis of covariance, we can compensate for its effect. We'll talk about that later in the course. And then another nuisance factor is noise. It's a factor that varies naturally and uncontrollably in the process, but can be controlled for purposes of an experiment. Such it may be like humidity. You may not be able to set the humidity, but while you can conduct an experiment fast enough to where the humidity doesn't change significantly during it. And so thus we control it during the experiment. Okay, so we need to choose an experimental design, and we'll talk about those later in the course. And then we need to conduct the experiment. And after we've conducted it and collected the data, we need to analyze the data. And using that statistical analysis, expertise, and knowledge, we need to draw conclusions and make recommendations to management or to the process owner. Okay? So, make sure we get here's some advice. Make sure you get the statistical thinking involved early in the designing of experiments. And this is the biggest thing that happens, is that people will design the experiments without the people who know statistics, and they'll get the results, and then they'll bring it to statisticians and say, we can't analyze this for us. And many times it's garbage, and we can't fully analyze it or give them the results they want to get from that data. But also remember that these subject matter experts, the non-statistical knowledge is still crucial to success. Neither group, the statisticians nor the subject matter experts, can do this by themselves. You need a group project here, or a group experiment. You need input from many different areas to be successful. And these pre-experimental planning steps, 1 through 3, these are vital to the success. Okay? If they're not done well, you're going to create waste, frustration, error, and maybe cost a lot of money unnecessarily. So it says think and experiment sequentially. So use logic is what I would say here. And then they say the KISS principle. This kind of tells our age when we say this. This says keep it simple. There was another S, but back in the 80s or when this came out, or maybe even the 70s, people would be kind of derogatory, so we won't use that second S. We'll just say keep it simple. Keep it as simple as possible, but not too simple, okay? So keep it simple principle. So think logically and sequentially. Okay, so that's it for this chapter 1. If you have questions, come to virtual office hours. If you need help before then, before you can come to office hours, if it's urgent, then by all means email me. I am happy to help you as soon as I can. Please take care of yourself, and we will see you next time.